Welcome to today class of nonlinear vibration. So, last class we have discussed on these static and dynamic static bifurcations, and there we have studied about the stability and bifurcation analysis of nonlinear fixed point responses. Today we will make more discussions on this saddle node, pitchfork and transcritical bifurcations, also on Hough bifurcation, which is a dynamic bifurcation. So, the static bifurcations are saddle node, pitchfork and transcritical, and dynamic bifurcation is Hough bifurcation. So, before discussing that thing, let us review what we have studied before. So, we studied about the solution of the equilibrium points. So, equilibrium points are the fixed points. For example, in this equation x dot equal to f x m, where m is the control parameter and x is the state variables. So, to find the fixed point, we are first equating the terms with time derivatives equal to 0, that means x dot equal to 0, and if it is x double dot also, if x double dot term, that is acceleration terms, are also there, then we may put that thing also equal to 0. So, in this first order equation, so we can write this x dot equal to 0. So, it will reduce to f x m equal to 0, from which we will get this value of x, which will correspond to the equilibrium positions. So, whether these equilibrium positions are stable or unstable, so that thing we can solve by linearization near the equilibrium position. So, or we can perturb the solution near this equilibrium position x equal to x 0, and we can find the Jacobian matrix, and finding the eigenvalue of the Jacobian matrix, we can tell whether the system is stable or unstable. So, for that purpose, so we can perturb the solution, let x 0 is the equilibrium solution, then we have given a small perturbation y t to the solution, and we can write this x t equal to x 0 plus y t. Then this equation, substituting this equation in the original equation x dot equal to f x m. So, we can write this y dot equal to f x 0 plus y m 0, and so we can write this y dot equal to d x f x 0 m y or a y, where A is the Jacobian matrix of the system. So, now finding the eigenvalue of this Jacobian matrix, so we can study the stability of the system. So, in this case already we have discussed how to find the stability. So, now by perturbing this thing, so as we have this equation y dot equal to a y. So, as t tends to, so here as t tends to t tends to 0, so y will tends to y 0, and in this case, so we have this, we can write this dy by dt. So, this is dy by dt equal to a, or dy by y will be equal to a dt, or if we integrate this thing, so we can have this ln y will be equal to a t, or we can write this y equal to e to the power a t plus a constant, or the solution we can write it equal to e to the power, we can write this thing equal to e to the power t minus t 0 into a, or this thing can be written as j equal to 0 to infinity t minus t 0 to the power j factorial into a to the power j. So, this is the solution of the, so one can get the solution from this equation. So, if the real part of this eigenvalue is negative, then exponentially it will decrease and one can obtain. So, if one plot y versus, so if one plot this y versus t curve, so it will exponentially decrease. So, if this real part becomes negative and if real parts is positive, so then the response will grow exponentially and one can get a unstable solution. So, to get stable solution, the real part of the solution should be, real part of the eigenvalue of a should be negative. So, now we obtain the solution y equal to e to the power t minus t 0 a. So, which is equal to j equal to 0 to infinity t minus t 0 to the power j by j factorial into a to the power j. So, if the eigenvalues lambda I of the matrix A are distinct, then there exists a matrix D. So, then there exists a matrix P. So, that is known as the modal matrix, equivalent, this is equivalent to the modal matrix. So, there exists a matrix P such that this P transpose P inverse, or one can write this P inverse. We can take this P in such way that this P inverse A P. So, this is a diagonal matrix which is D. So, we can find a matrix P, we can select a matrix P such that, so P inverse A P will be equal to D. So, this will happen if all the eigenvalue of this matrix lambda I are distinct. So, if you have a distinct eigenvalue, if all the eigenvalues of A, which are lambda I are distinct, then we can have a matrix P such that we can write this P inverse A P equal to D. So, in this case, we can write, let lambda 1, lambda 2, and lambda n are the distinct eigenvalues. Then we can write this D matrix equal to, so this is D 1 0 0. So, 0 lambda 2 all zeros. So, similarly, we can have 0 0 lambda n. So, we can obtain a matrix P such that we can write this D equal to P inverse A P equal to D, where D is this matrix. So, for now we can write, so this y equal to, so we can write y equal to, we have this P. So, we are taking P inverse A P equal to D, P inverse A P equal to D, or we can write as we can take this y equal to, let us take y equal to P into V, then this y dot equal to A y will reduce to, so y dot will reduce to P V dot equal to A P V, or we can write this A P V. So, here I can write from this equation, I can write this A P will be equal to P D. So, as A P equal to P D, so I can write this P V equal to P D V, or we can write this V dot equal to D V. So, we can write this V dot equal to D V, and from this also we can get this distinct, as lambda are distinct. So, we can write the solution in a distinct form. So, by using this V dot equal to D V, so we can write the solutions, and we can. So, in this case, if the eigenvalues are complex, then the matrix P will also be complex. The column of matrix P are the right eigenvectors of P 1, P 2, P n. So, this P can be written as P 1, P 2, P n. So, we can write this P matrix equal to P 1, P 2 and P n. So, this A P can be written as A into P can be written as A P 1, A P 2, A P n. So, we can write, so from this way we can get this A P, and already we have shown that this A P can be will be equal to P D, P into D. So, D the diagonal matrix which is in this form lambda 1 0 lambda. So, the diagonal terms contains all the eigenvalues. So, in this way we can write this V dot equal to this. So, as our V dot equal to D V, so the solution V will be equal to, similar to the previous case. So, the solution V will be equal to e to the power t minus t 0 into d V 0. So, we can write when V0 equal, so where V0 equal to V at t equal to T0. So, this can be written also equal to P inverse y T0. So, we can write substituting this in our original equation. So, we can write this y t equal to P e to the power t minus T0 d into P inverse y T0. So, the advantage of using this equation is that d is a diagonal term. So, the matrix e to the power t minus T0 d is a diagonal matrix with entries e to the power t minus T0 lambda I. Hence, the eigenvalues of A are also called the characteristic exponents associated with f. So, in this way we can find the solution y t. So, y is the perturbation we have taken. So, if this perturbation grows, then the systems will be unstable, and according to our Lyapunov principle. So, if it remains within a bounded region, then the solution will be stable. So, let this is the equilibrium solution. So, if we are perturbing this thing and it is remaining within this circle or in this bounded region, then the systems become stable, and if it grows. So, we have taken a point and it grows. So, if it grows with time, then it becomes unstable. So, for the system to be stable, so it should remain within this region. So, if you perturb it or if you start the solution nearer to this point, always it should come to this solution point. If it takes infinite time to come to the solution, then it is asymptotically stable, but if it remain within this state, then it is within the circle, then it is stable. So, we have stable and unstable solutions, and in this case we have seen when we have taken the distinct eigenvalues. So, instead of distinct eigenvalues, if some of the eigenvalues are not distinct, then there exists a matrix P such that, so we can find a matrix P such that this P inverse A P will be equal to J, which is known as Jordan canonical form. So, this is Jordan canonical form. So, we can write the system using this Jordan canonical form, where this J equal to J1 phi. So, this is phi. So, let us assume there are k distinct eigenvalues. So, we can write this phi, and finally, it will be phi j k. So, here we are assuming that we have k distinct eigenvalues. So, here this j m can be written as lambda m 1 0 0 0 lambda m 1 0. So, all are 0. So, here we have lambda m. So, here one can find this j m will contain this 1 above the diagonal terms. So, above, for example, in this second diagonal, so this is lambda m. So, above that thing, so this is lambda. So, above this, so we have a term that is 1. So, this J m matrix is not diagonal, as we have this entry is 1 in the just above the diagonal terms. So, here we are assuming that we have k distinct eigenvalues, and let us also assume that the multiplicity of this mth eigenvalue, that is J m, mth eigenvalue lambda m, let the multiplicity of mth eigenvalue lambda m be n m. For example, let us take, we have total 15 eigenvalues. So, out of these 15 eigenvalues, let us we have 10. So, k will be equal to 10. So, let us have k 10 distinct eigenvalues. So, for example, distinct eigenvalues will be 2, 5, 7, 6, 8. So, we can have, so let n equal to 10. Let us take example where we have total 10 number of eigenvalues, out of which 5 are, so 5 are distinct. So, 5 distinct 2, 5, 6, 2, 5, 7, 6, 8. So, these are distinct eigenvalues. So, here k equal to 5. Now, let us take, so the first, so let us take, this is 3, this is another eigenvalues 3, 3. So, this is repeated. So, here it is repeated twice. Another eigenvalue let us take 4, 4, 4. So, here it is repeated 3 times. So, here m equal to, so in this case m equal to 2 and in this case m equal to 3. So, the multiplicity in this case equal to 3, that means this eigenvalue, that lambda equal to 4, lambda m equal to, so I can put m equal to here lambda 1 equal to, so this is 3 and 3. So, this is repeated, here also it is repeated. So, this eigenvalue repeated 2 times and this eigenvalue repeated 3 times. So, in this case let us assume that this lambda m eigenvalue have this multiplicity n m. So, if lambda m eigenvalue has multiplicity n m, for example, in this case the 6th eigenvalue has multiplicity 2 and the 7th eigenvalue has the multiplicity 3. So, we have k distinct eigenvalues. In addition to that, we will have some other eigenvalues which has repeated roots. So, in that case let n m be the multiplicity of this lambda m. So, the matrix J m corresponding to the eigenvalue lambda m. So, differs from the distinct eigenvalue because we have this entry 1 just above the diagonal term. So, in this case the column p I of the matrix P are called generalized eigenvectors corresponding to the eigenvalue lambda I of matrix A. So, there are n m. So, we will have n m generalized eigenvectors corresponding to the eigenvalues lambda m. So, these eigenvectors are, the non-zero solutions of, so they will be non-zero solution of A minus lambda m I p equal to 0, then A minus lambda m I square p equal to 0. Similarly, it will continue A minus lambda m I n m p equal to 0. So, by solving these equations, so we can get these values. So, the corresponding V will be, so in this case the corresponding V we can get. So, it will be in this form t to the power k e to the power t minus t 0 lambda I. So, the corresponding value of V will be equal to t to the power k e to the power t minus t 0 into lambda I, where the integer k, so t to the power k what we have taken. So, this integer k depend on the multiplicity n I of the eigenvalue lambda I. So, for example, let us take a simple example. In case of a simple examples, okay. So, let us take the simple single degree of freedom system. So, our equation x double dot plus 2 zeta omega n x dot plus omega n square x equal to 0. So, this equation I can write in this form, x dot equal to y and y dot equal to minus 2 zeta omega n x dot minus omega n square x. So, taking zeta equal to, let zeta equal to 1. So, in this case we know we will have repeated roots. So, our equation will reduce to, so x dot equal to y and y dot becomes minus 2 omega n y minus omega n square x. So, here our state vector are x and y. So, these are the state vector. So, from this equation, so I can write the Jacobian matrix A. So, Jacobian matrix A will be equal to, so this equation can be, so we can differentiate this thing as x term is not there. So, first derivative, so this becomes 0 and this is 1, and in this case, so this becomes, this is minus omega n square x. So, differentiating with respect to x will give minus omega n square and differentiating this thing will give you minus 2 omega n. So, A becomes 0 1 minus omega n square minus 2 omega n. So, our auxiliary equation or eigenvalue to, we can obtain the eigenvalue by taking the determinant of A minus lambda I equal to 0. So, by taking that, so what do we got? So, we got this lambda square plus 2 omega n lambda plus omega n square equal to 0. So, from this we have seen that lambda 1 equal to minus omega n and lambda 1 and lambda 2 also equal to minus omega n. So, according to this our solution becomes, so that is our y solution becomes. So, the solution we can write, or x we can write equal to t into e to the power minus t 0 omega n. So, the formula what we have derived before. So, this is, so using that formula. So, or directly also from this case we can write the solution will be. So, the solution we can write. So, the solution y will be equal to, so we can write the solution y equal to C 1 e to the power. Okay, so, we can write in two different form. So, we can write this thing also A 1 t plus b into e to the power minus omega n t. Here we have two constant A 1 and b, or we can write that thing in this form also. So, this is our perturbation. So, if our perturbation, so this is x dot equal to y and y dot equal to x. So, we can write this perturbation and that is our v. So, this v will be equal to, so in this form. So, v will be equal to A 1 t plus b e to the power minus omega n t, or it can be written in this form, the solution t e to the power minus t 0 omega n. So, this is the perturbation. So, the perturbation delta y. So, if I am writing this equation whole equation as y dot equal to a y, then the perturbation will, this is the Jacobian matrix. So, from this Jacobian matrix we can find the solution, and the from the solution. So, this will be our delta y. If delta y is the perturbation of y, then this becomes delta y, or I can take it v also. Delta y becomes this. So, in this way one can find. So, this is the perturbation. If this perturbation grows with time, then the system becomes unstable, and if it remains within the limit, then it becomes stable. So, in this way one can find the stability of the system by perturbing the given differential equation. So, here we have taken a simple second order differential equation, then we have converted the second order differential equation to a set of first order differential equation, and just by perturbing this thing we can obtain the Jacobian matrix, and this Jacobian matrix can be, so it can be solved, that is A minus lambda I. So, if we put A minus lambda I, determinant of A minus lambda I equal to 0, where lambda is the eigenvalue of the system, then we can get the solution, and if we have repeated roots, then the solution will be, so for that the solution will be this, and if this perturbation grows, then the system will be unstable, otherwise it will be stable. And again last class we have discussed about different bifurcation points. So, these bifurcation points are static bifurcation point and dynamic bifurcation point, and in case of static bifurcation point we have seen the saddle node bifurcation point, pitchfork bifurcation point and transcritical bifurcation points. So, in case of saddle node bifurcation point, let us discuss about the static bifurcation. So, in case of static bifurcation, so we have, we have a system. So, if we have the system x dot equal to f x alpha. So, if this is our system, let us consider a first order system only, which we can extend easily for the higher order system. So, in this case, if our system is x dot equal to f x alpha, where alpha is the control parameter, then so the bifurcation point. So, to find the static bifurcation point first, so it should obey that this f, the first point will be f x alpha. So, x 0 alpha 0. So, let alpha 0 is the bifurcation point. So, then x 0 alpha 0, so must be equal to 0. That means, this substituting this x dot equal to 0, where x 0 is the equilibrium solution. So, in this x alpha control space, so if you plot this x alpha, so corresponding to this alpha 0, so if x 0 is the bifurcation point, then this f x 0 alpha 0 should be equal to 0. The second point should be this dxf, which is the Jacobian matrix. So, this dxf has a, so it should have a 0 eigenvalue. So, it should have a 0 eigenvalue, while at least one eigenvalue should be 0. So, dxf has a 0 eigenvalue, while all other eigenvalues are non-zero real parts, 0, while other eigenvalues have non-zero real parts. So, at least one of the eigenvalues should be, or dxf has a 0 eigenvalue corresponding to this alpha equal to alpha 0. So, these are the necessary conditions for the system to be, so the system to have a static bifurcation point. So, these to be the necessary condition, but these conditions may not be sufficient. So, to distinguish the saddle node bifurcation point from other bifurcation point, so we should find this f alpha. So, find f alpha. F alpha is the differentiation of f with respect to alpha. So, and then let us construct a matrix with dxf and f alpha. So, if we construct a matrix with dxf and f alpha, and if at the saddle node bifurcation point, so one can show that, so this f, so we can find this f alpha. Now, so this, if this, so this will be, let us take this example, so then it will be clear. So, let us take this example x dot equal to f x mu. So, where this is equal to mu minus x square. So, in this case we can write this. So, at equilibrium point x dot will be equal to 0. So, mu minus x square equal to 0, mu minus x square equal to 0, and in this case we can find this x will be equal to plus minus root over mu. So, x will be equal to plus minus root over mu. So, if we can plot this curve, that is already we have plotted several times this curve. So, this is equal to, so x and mu if I will plot. So, for mu value of negative value of mu, so x will be imaginary. So, it will have no solution for x equal to, for negative value of mu, and for positive value of mu. So, we have two solutions. So, in this case we have two solutions, and these two solutions, let us discuss about the static bifurcation point. Already we know the saddle node bifurcation point, pitchfork bifurcation point, and transcritical bifurcation points are static bifurcation point. In static bifurcation point, it should satisfy two conditions. First condition, so for this first order system x dot equal to f x alpha, where alpha is the control parameter. So, this f x 0 alpha 0 should be equal to 0. So, here x 0 is the solution corresponding to alpha equal to alpha 0, and x 0 is the equilibrium solution. So, here dxf has a 0 eigenvalue, while other eigenvalues have non-zero real part. So, to check whether this static bifurcation point is a saddle node bifurcation point or other different type of bifurcation point, we should construct a matrix with dxf and f alpha, where f alpha is the first derivative of f with respect to alpha, and if this f alpha belongs to the range of A. So, if this f alpha belongs to this range of this matrix, then so if f alpha belongs to the range of matrix A, then we can tell that this is other type of bifurcation. If f alpha does not belong to R A, then it will be a saddle node bifurcation point. So, for example, in this case, let us take the example of this x dot equal to f x mu equal to mu minus x square. Here the solutions or the equilibrium points will be obtained by putting this x dot equal to 0, that means mu minus x square equal to 0. So, x becomes plus minus root mu. So, at mu equal to 0, so this is corresponding to 0. So, mu equal to 0. So, we have x equal to 0. Here a equal to, so by finding the first derivative, so we can find this a equal to minus 2x. So, as a equal to minus 2x, so a minus lambda I can write this equal to minus 2x minus lambda equal to 0, or this. So, we can write this thing. So, lambda equal to minus 2x. So, the eigenvalue becomes minus 2x. So, at mu equal to 0, so x equal to 0, so we will have a 0 eigenvalue. As we have a 0 eigenvalue, so it satisfies the second condition, that is dxf has a 0 eigenvalue, and also the first condition is satisfied at mu equal to 0. So, mu equal to 0 correspond to this static bifurcation point. So, at static bifurcation, so this point, that means this origin is a static bifurcation point at its, as it satisfies both the condition, that is f x 0 alpha 0 equal to 0 and dxf has a 0 eigenvalue. So, now as this is a, so let us find what is our, so now f alpha equal to, so our, so let us construct the matrix dxf. So, we have to construct the matrix dxf and f alpha. So, dxf is nothing but our A and f alpha. So, here f alpha will be equal to our f equal to, so f equal to mu minus x square, as f equal to mu minus x square. So, f alpha, so here alpha is nothing but our mu. So, f mu equal to, so we can find this f mu. So, f mu equal to 1. So, if you differentiate this with respect to mu, so we have f mu equal to 1, but our A equal to, so already we have found this A. So, A equal to A at this point at x equal to 0, our A becomes, so A equal to minus 2x. So, A equal to at x equal to 0, A becomes 0. So, our this matrix f dx alpha, so this matrix becomes, so 0 1. So, this matrix f alpha matrix becomes 0 1, which has a rank. So, this has a rank of this matrix. So, this has the rank of 1. So, the origin x minus mu is a saddle point, saddle node point, as f alpha, that is f alpha equal to 1 does not belongs to this A is only 0. So, as this does not belongs to this, so this point is a saddle node bifurcation point. So, the saddle node bifurcation point also can be distinguished with from other bifurcation point, as at this point. So, the at this bifurcation point we can have same tangent from both the sides. So, by studying the stability we can see. So, let us see about the stability of these two branches. So, for this branch let us take a point on this branch. So, that means this is positive. Let us take mu equal to positive. So, if mu is positive, then this lambda becomes minus, as x equal to root over mu. So, let us take mu equal to 1, for example mu equal to 1. So, then x becomes plus 1 and minus 1. So, for plus 1 x, when x is plus 1, so lambda becomes minus 2. So, lambda is corresponding to this point, lambda is minus 2, corresponding to this point, lambda is minus. So, if it is 3, minus 3. So, eigenvalues are negative. So, as eigenvalues are negative, so this branch is a stable branch. So, this branch is a stable branch, and for this branch, so let us take a point here. So, let this correspond to minus 1. So, if mu equal to minus 1, so x becomes minus. So, if mu equal to, so let us take this, no. So, this correspond to mu equal to 1, but x equal to minus 1. So, as x equal to minus 1, so our lambda becomes minus minus plus 2. So, as lambda becomes positive, so on this branch lambda value, so for corresponding to x equal to minus 3, this becomes plus 3, this becomes plus 5. So, these points becomes negative. So, these point correspond to negative eigenvalue, this point correspond to positive eigenvalues. So, as this point correspond to the positive eigenvalue, so I can plot dotted line here instead of solid line, I can plot a dotted line, and this branch becomes unstable branch. So, in this case we have seen we have a stable branch and another unstable branch. So, they meet at the origin. So, these two branches meet at the origin. So, already we have plotted this curve here. So, this is the stable branch and this is the unstable branch, and the stable and unstable branch meet at this point. So, this is the saddle node bifurcation point. So, the normal form or generic form of this saddle node bifurcation point for a first order equation is x dot equal to mu minus x square. Similarly, one can consider two equations also second. So, we have a second order equation, or we can reduce that thing to a set of two first order equation. So, if I have two first order equation, so by finding the eigenvalue, so first one can find the Jacobian matrix A, and then one can find the Jacobian matrix corresponding to this point. One can observe that corresponding to this point, it should have a eigenvalue equal to 0. So, this point and this point are found to be. So, by checking the eigenvalue, one can see. So, this branch is unstable and this is a stable branch. So, the stable and unstable branch meet at this point. So, one can see the slope at this point are same for both stable and this unstable branch, and so these two. So, this point is a saddle node bifurcation point, and in this case by finding A, which is the Jacobian matrix, find the eigenvalue, check at what point by changing this control parameter. So, this is the control parameter. So, by changing these control parameters, check at what point the eigenvalue changes from positive to negative or negative to positive, or it has a 0 eigenvalue. So, by finding that point where it has a 0 eigenvalue, we can tell that correspond to a critical point or a bifurcation point. So, in this way one can find the saddle node bifurcation point. So, in case of saddle node bifurcation point, we have to construct the DXF and F alpha matrix, and we have to check whether this F alpha belongs to the range of A. So, if it does not belongs to this range of A, then we can tell this is a saddle node bifurcation. Otherwise, it may be a transcritical or a, so either it may be a transcritical or it can be a pitchfork bifurcation point. So, let us see the generic form of the pitchfork bifurcation point. So, the generic form of the pitchfork bifurcation point can be written in this form. So, the generic form of pitchfork bifurcation point is mu x minus x square equal to x dot equal to this. So, x dot equal to mu x minus x square. So, in this case we have, so by putting this x dot equal to 0. So, let us take this example, x dot equal to mu x minus x square. So, by putting this equal to 0, so we can write this x into mu minus x. So, for pitchfork bifurcation, so it will be mu x minus x cube. So, for pitchfork bifurcation we have mu x minus x cube, and transcritical bifurcation point we have mu x minus x square. So, in this case, so x into mu minus x square equal to 0. So, here x equal to 0 is the trivial solution. So, we have a trivial solution, and mu minus x square equal to 0. So, this is non-trivial solution. So, we have a set of trivial solution and a set of non-trivial solution. So, in this case, if one plot this, so one can say, see, so for example corresponding to this, so we can have this, and corresponding to this case if we will plot, so we have a 0 solution, and then we have a solution like this. So, this 0 solution, let us see this point. So, our A equal to, so in this case the Jacobian matrix, so we can find the Jacobian matrix A. So, A can be obtained by differentiating this with respect to x. So, differentiating this with respect to x gives A equal to mu minus 3 x square. So, A minus lambda I, so we have to find A minus lambda I, determinant of A minus lambda I equal to 0. So, from this we can find, so mu minus 3 x square minus lambda equal to 0, or we have this lambda equal to mu minus 3 x square. So, corresponding to our x equal to 0. So, I can plot this curve in x mu. So, let us plot this curve. So, this is x and this is mu. So, we have seen okay. I'll take this thing. So, x equal to mu, and we can so this is 0 line. So, we can have a 0 line, and we can have this other line also. So, in these cases we can plot this line, so trivial and non-trivial state. So, this is the trivial state x equal to 0, and this line, this curve becomes x equal to non-zero. So, for mu x minus x cube. So, now this is the solution. So, now substituting x equal to 0. So, we can find lambda equal to mu. So, x equal to 0 correspond to lambda equal to mu. So, when mu is positive, so if mu is positive, then lambda is positive. So, the eigenvalue becomes, positive. So, this branch becomes unstable. So, this to this branch becomes unstable. So, I can have this branch unstable, and corresponding to mu negative. So, corresponding to mu negative, so lambda becomes negative. So, this branch becomes stable. So, I have a stable trivial branch x corresponding to negative eigenvalue. So, this is stable branch. So, at x equal to 0, so at x equal to or mu equal to 0, at mu equal to 0 lambda becomes 0, that means one of the eigenvalue becomes 0. So, this correspond to a static bifurcation point. So, at this static bifurcation point, so we have this stable trivial branch and unstable trivial branch meet at this point. So, along with this we have another two solutions, that correspond to x mu minus x square equal to 0. So, let us take mu equal to 1. So, if you take mu equal to 1, so we will have, so if mu equal to 1, so what we will have? So, we will have x square equal to mu, or this is equal to 1. So, x will becomes plus minus 1. So, as x becomes plus minus 1 corresponding to mu equal to 1. So, we have x equal to plus minus 1. So, our lambda, so let us consider the plus. So, this point, so which correspond to x equal to 1, then in this case, so lambda becomes for mu we have 1. So, minus 3 x square. So, 3 into 1 square. So, this becomes, so 1 minus 3. So, 1 minus 3 this becomes negative. So, as it becomes negative, so we can have a, this is a stable branch. Similarly, this is also a stable branch. So, here what we have observed, so from a stable trivial branch, we have other two stable non-trivial branches. Along with that, we have a unstable trivial branch. So, after this bifurcation point, the number of solution increases. So, before this bifurcation point, we have only a single solution, but after this bifurcation point, we have 3 solutions. So, 1, 2, so this is 1, this is 2 and this is 3. So, out of these 3, so 2 branches are stable and this branch becomes unstable. So, if we increase this mu value, let we have increased this mu value from this side and we proceed. So, then we will have a solution along this line and then either it may proceed this way or this way. So, it will have a stable solution. So, as this branch is unstable, as the trivial branch is unstable, actually the system will follow the, so the system will follow the stable branch. So, this is a supercritical pitchfork bifurcation point, supercritical pitchfork bifurcation point. So, in case of supercritical pitchfork bifurcation point, so from a stable branch we have another stable branch and unstable trivial branch. So, this is known as this forward bifurcation point. So, we can have a backward bifurcation point also. So, we can have a backward bifurcation point corresponding to this. So, for example, if we take, so if we take this x dot equal to mu x plus x cube. So, let us take this example mu x plus x cube. So, in this case we will have this taking this x common. So, this is mu plus x square. So, our f x mu equal to x into mu plus x square. So, this equal to 0. So, x, the solution becomes x equal to 0, one solution, and the other solution becomes x square equal to minus mu or x equal to plus minus root over mu. No. So, plus minus. So, the solution becomes plus minus. So, we have x square equal to minus mu. So, this is minus mu. So, if we want to plot the solution in this x mu, so this is x and this is mu. So, if we want to plot this curve, so in this case we have, so for the negative mu, so negative value of mu, so this term becomes positive. So, we will have 2 positive solution and also this is the trivial solution. So, we will have, so the solution becomes this. So, we have a trivial branch and these 2 are non-trivial branch. So, in this case our A matrix, that is our Jacobian matrix becomes. So, if you differentiate this thing, so x mu x plus x cube. So, differentiating this thing we have this is equal to mu plus 3 x square. So, for this trivial branch, so for the trivial branch we will have A equal to mu. So, as A equal to mu is for trivial branch. So, when mu is negative, so as mu is negative, so this, so our A minus from A minus lambda I equal to 0. So, we know this mu minus lambda equal to 0. So, or lambda equal to mu. So, as lambda equal to mu is the eigenvalue. So, for negative value of mu, so for the negative value of mu, that is from these to this position. So, we have a stable branch. So, this is stable, and after the solution, after this branch, so that means we can erase this thing, and up to this we have a stable branch, and we can see. So, for positive value of mu, so we have a positive eigenvalue, as positive eigenvalue is unstable. So, we have a unstable solution. So, this side is unstable solution, unstable trivial. So, this is unstable trivial state, and this is stable trivial state. So, this is stable trivial, this is unstable trivial. Now, correspond to any point, let us take x equal to +1 or -1. So, corresponding to this, so our A becomes, so for x equal to, let us take x equal to +-1. So, these 2 points. So, in this case A or lambda will, so A minus lambda I equal to 0. So, this lambda becomes, so lambda equal to mu plus 3x square. So, as mu, so let us take this mu equal to -1. So, corresponding to mu equal to -1. So, corresponding to mu equal to -1, we have x equal to +-1. So, this 3x square, this becomes 3 into 1. So, this becomes 3. So, this becomes +2. So, now this becomes +2. So, 3x square, let us check it again. So, lambda equal to mu plus 3x square, as mu I have taken -1. So, corresponding to mu equal to -1. So, x becomes, so x becomes root over +-1. So, 3x square. So, 3x square becomes 3. So, then this becomes +2. So, as this is positive, so this branch is unstable. So, we can have a unstable branch. So, initially, so this is unstable. So, at this bifurcation point, what we have observed, we have a stable trivial state along with 2 unstable non-trivial state, and after the bifurcation, so this branch becomes unstable. So, this type of bifurcation is, as there is no solution after this, so there will be a catastrophic failure of the system, and this type of solution are known as subcritical pitchfork bifurcation point. So, this becomes subcritical pitchfork bifurcation. So, this type of bifurcation what we have studied with here. So, these are pitchfork bifurcation. So, this is one pitchfork bifurcation, this is one pitchfork bifurcation. So, we have subcritical pitchfork bifurcation and supercritical pitchfork bifurcation. So, at this point one see, so from a stable branch we have a stable branch. So, then this is supercritical pitchfork, and here from a stable branch we have unstable branch. So, this is a subcritical pitchfork bifurcation. So, today class we have seen this, we have discussed more about these saddle node bifurcation point and pitchfork bifurcation point. So, next class we will study about the Hopf bifurcation point, which is a periodic bifurcation point generated due to this dynamic bifurcation, and along with that we will study the solution of periodic response. Thank you.